Okay, Bismillahirrahmanirrahim. Assalamualaikum warahmatullahi wabarakatuh. So let's continue our chapter 2. So this will be your last part of chapter 2. So we're moving from semiconductor to what we call diode. Okay, so let's recall what have you learned last class. So you learned about how we can build P and N junction. So from this P and N junction where you can have what we call a diode. So what is the function of diode? To allow the currents to flow in only one direction. So here will be plus, here will be minus. So you will have the what we call diode current and then diode voltage. Okay, number one. The term number one is the built-in potential. So what is built-in potential? The minimum energy required to pass what we call here depletion region. So it depends on what we call here V thermal. So if it is at room temperature, your VT will be 0.026 volt. Lon, this is acceptor, this is donor from N type, this is from P type, and this is from intrinsic. Okay. So when you apply here positive, minus, positive, negative, so this will be forward bias. So when your positive is connected to your P and negative connected to the N, so this will be forward bias and then you can get the current. You can get the currents. So what is the formula for the current? Is this formula. Okay. What will happen at the reverse bias? So here let's say your PN and here you're going to connect to minus, plus, minus, plus. And then it will be attracted and then the depletion region become bigger, right? So you will have what we call charge inside here. So that's where in your reverse bias, you will have what we call junction capacitance. So what will be the formula for junction capacitance is this formula. Okay, so next we will leave the semiconductor, PN junction, all the physics term behind. So what we will be focused now is your diode. So in your diode, you have two analyses. One we call DC analysis, another one we call AC analysis. If you recall back chapter 1, so chapter 1 you learn about DC and AC. What is the function of DC? If diode is an active or passive. So diode is an active device. So what does it mean by active device? You need the DC supply to turn on. And you need the AC supply to operate the device. Okay, so in your DC supply you are going to denote with capital or small, so it will be all capital. In your AC will be all small. So at the end, how you going to combine the total? Small I capital D equal capital I capital D plus small I small d. So this is DC, this is AC. So we go through one by one. So the first one we learn about DC analysis, and then the second one we will learn about this AC analysis, and you will also learn about the load line where it is from the graph. So the learning outcome for this chapter is first you need to be able to analyze what we call DC analysis, AC analysis, and the other term is load line. Okay, why we need DC analysis? As I mentioned before, we need because this is diode is a active device, so we need to turn on the device. So in your DC analysis, you need to find all its capital, that is ID and VD. Okay, now we focus on DC analysis. So there are three methods to find the value of DC analysis. Your final aim is you want to find diode current and voltage current at the DC analysis. Okay, the first one is what we call direct approach. The second one is the mathematical approach, where we're going to do some assumption here. And the third one where the term load line comes from, where we call this one graphical approach. So it need to be based on the graph that you learned last class. There is ID and VD. So how is the shape of the graph? Forward bias is after some voltage. So this is a built-in voltage. You will have some current. So this is forward bias. Less than the VBI, so we call this one reverse bias. So you need to have some line here where we call load line in order to find ID and VD. Okay, so let's go through the first one, direct approach. Okay, the circuit given for this chapter we have one supply, so we call this one DC supply, one resistor. So resistor, we have the polarity here must be plus, here must be minus, and it will be connected to one resistor. So why we need to connect this resistor? To limit the current, because you want to protect your diode. So if you accidentally apply here very high voltage, it will not damage the diodes. That's why you need to always connect to a resistor. So all these components are in series. So your aim again, you want to find the diode current and the diode voltage. So now let's go through the equation. So what is the equation for this circuit? In order to find ID and VD, so you need to apply what we call KVL equation. So let's say we start KVL from here, become minus VPS plus this RD ID plus VD equal to 0. So you rearrange this one, so it become ID equal VPS over RD minus VD over RD. Okay, so RD here means R here. So you can get the same here. ID equal VPS over R minus VD over R. So your argument will be in terms of equation. So in your previous chapter, you learned about the diode equation current, right? So if you see here, this one is the equation that you have seen before. ID equal IS, reverse saturation current, exponent VD over VT minus 1. So what you need to do now, you need to plug in this equation number 2 into equation number 1. So let's try to put it together. So it become IS. This RR, right? So you move R at the other side. So it become ISR E VD over VT minus 1, right, equal to VPS minus VD. If you rearrange this one, and then you can get this equation. So let's see the unknown here. So what is the unknown here is, you have VD1 inside here, the other one is outside here, right? And here is your VPS. So there are two VD location, one is inside and one is outside. And in this equation, you are given VPS equal to 5, RS will be given, R is 2K, VT is room temperature 0.026 volt. So now there is one equation, but you have two location of unknown. So this one is become very quite difficult to solve. But we can conclude here, difficult to solve. So if you see the next slide, okay, so this is what we call direct approach. So if you have the previous equation just now, so this will be your equation when you already plug in all the value. So you have two location of VD, one is inside, another one is outside. So how you're going to solve this one is what we call iteration method. So it's quite long steps to go. So we can consider this one is difficult to solve, but you still can solve it until you got this value. Okay, so since method 1 just now is difficult to solve, right? So let's move to the method number 2, that what we call mathematical approach. So in this approach, we are doing some assumption. So we have three models. This one is V gamma, and V gamma. Okay, so the three models that will be called ideal model. The first one, piecewise linear model 1 and piecewise linear model 2. So why you need this mathematical approach? Because you want to simplify the analysis, because the previous method just now is quite difficult to solve. So again, what is V gamma here? V gamma we can denote as turn on voltage, or as you learned before is what we call VBI. So if we draw the graph, this is the graph of the diode, right? ID and VD. Which one will be forward bias? Here will be forward bias. What is the minimum voltage to turn on? This is what we call V gamma or VBI. So it will depend on the value of V gamma here in order for you to solve the mathematical. Okay, so let's go the model number 1, that is ideal model, where you're going to denote V gamma equal to 0. So what does that mean? Ideal model means you don't have any turn on voltage. Your turn on voltage is equal to 0. Means if you plot the IV characteristic, the turn on voltage is 0. So it means in a very perfect condition, there will be no built-in voltage. So now let's see what happened at the reverse bias. So this will be your reverse bias. So your input will be connected to minus, plus. So at here, at first you will have a diode, right? So let's say this is the circuit. You connect here minus, plus, and what will happen? Here is plus minus, right? So the diode will be turned off. The diode will be turned off, so it will be open circuit, and there will be no current flow at the reverse bias. How about at the forward bias? At the forward bias, where you're going to apply here, again this is a diode. You start to apply here plus minus. So plus will be connected to P, minus will be connected to N. So your diode will become forward bias. But you're going to assume this one, your voltage drop at your diode will be equal to 0. What does that mean? It will be short circuit here. So this part will be forward bias. The left part will be reverse bias. We can see in the ideal model, when it is directly short circuit, means here your V gamma is equal to 0. So this will be forward bias. What happened at the reverse bias? It will be open circuit and you don't have any voltage here. Okay, so let's see the first question. Determine the diode voltage, this is VD, and the diode current ID in the circuit using ideal model. So the keyword here is ideal model. So keyword number 1, when it is saying ideal, the voltage drop inside the built-in voltage inside the diode will be equal to 0. So let's try to redraw the circuit. What happened during reverse bias? Reverse bias, where you start to apply here minus, plus, right? And then this will be turned off, and there will be no current. What happened during I equal to 0? What happened during forward bias? Here will be plus, and then here will be minus. Your diode will be turned on, right? So here become plus, minus, plus, minus. But your diode, when it is turned on, it will become short circuit. Why short circuit? Because your V gamma here is equal to 0. So how you can get the value of current here? I equal VPS over R. So you can get directly 5 divided by 2K, which is 2.5 milliampere. This is what you can get at the ideal model. Okay, the question we ask first is diode current. What will be the diode voltage? So please take note here, you are going to focus on the diode part. So where is the diode part? Between this point and this point is what we call VD. The diode voltage is not for the whole circuit, it's only focusing on the diode. So what will be the voltage drop across the diode is equal to 0. Okay. Number 1, it will based on diode current, diode voltage, and the number 3 is power dissipation inside the diode. Again, this is not power dissipation on the whole circuit. It is only inside the diode. So you're going to multiply VD or multiply by ID. So you will get 0 watt, 0 volt, and 2.5 milliampere for ideal model. So ideal model, reverse bias, no current. Forward bias, you're going to replace your diode. You're going to replace your diode with this one during forward bias with short circuit, where your V gamma is equal to 0. Okay, so this will be the end of the ideal model. Next video, we'll move forward to the model 2, that is V gamma. Thank you. Assalamualaikum.